This video is about chain rules and implicit differentiation. I'm just solving some problems from a quiz. And this is standard F15 in our class, I think. Let me check. Yeah, that's F15. Okay, so we are given a function of three variables. F of x, y, z is equal to this, and we're asked to find the gradient of f. Remember, the gradient of f is represented by del f. It's a vector whose components are the first partial derivatives of this function with respect to each of the independent variables separately. Since this is a function of three variables, our vector has three components. So we just want to find those three partial derivatives, then we'll substitute them in. So this is the partial derivative with respect to x of our function f, which is x times e to the y over z. Now, as far as we're concerned, when we're taking a partial derivative, y and z are being treated as constants. So this is really the derivative of a constant times x. The derivative of a constant times x we know is the constant. Then over here, I'm going to do the same thing, but this time with respect to y. Now, since y is our variable, it makes more sense to rewrite that exponent just a little differently. I'm going to write that as y times z to the negative 1. Now, x is just constant with respect to y if we're taking a partial derivative. So the derivative of this constant times a function of y is that constant times the derivative of the function of y. Now, this function of y has a function nested inside another function, so it requires the chain rule when we take its derivative. Derivative of e to some power is e to that power times the derivative of the inside with respect to y, treating x and z as constants by the chain rule. Now this is a constant times y. The derivative of a constant times y is just the constant. So we end up with this z to the negative 1 times that, or if you prefer, you can just put the z in the denominator. So we've got that. And then we'll do the same thing here. We'll take the partial of f with respect to z. And use that same rewrite that I used a second ago. This is a constant times a function of z, so we bring the constant down. And the derivative of e to some power, where that power depends on z, is e to that power times the partial derivative of the inside with respect to z, treating x and y as constants by the chain rule. And I end up with a constant times z to the negative 1. The derivative of a constant times z to the negative 1 is that constant times negative 1 times z to the negative 2 power. So we bring the power down and we multiply by z to the 1 less power. So you've got this negative factor multiplying this exponential over here. So I end up with a negative xy, and that z to the negative 2 I can write as a z squared in the denominator times our exponential. So that's the gradient, or those are the components of the gradient, that, and that. The gradient is a vector, so we're not done until we state our vector. Oops. So you can use this notation, or if you prefer, you can write everything in terms of I hat, j hat, and k hat, same thing. So I've got this component times I hat plus the second component times j hat plus the third component, which is negative, so we're subtracting the third component times k hat. Okay. So we really just compute those three partials. And then we substitute those into the form of the vector. Okay. Now the next part asks us to find r prime of t given a vector valued function r of t. Now it has components x of t, y of t, and z of t. Remember how we take the derivative of a vector valued function? We just take the derivative component by component. And of course, the derivative of t squared is 2t. Derivative of that factor, or that component, is -1, and the derivative of this component is 2. Okay. On the next page, we're asked to find the change in w with respect to t. Remember, w is that function of 3 variables that we were just looking at. It says, while not required, you may wish to use the gradient you found in 1a and the derivative you found in 1b. I think I will do that. The derivative of w with respect to t is the gradient of f, where w is equal to f of x, y, and z. But we want to evaluate this at x of t, y of t, z of t. Those are components of that vector valued function. So now I've got my gradient entirely in terms of t. If I take that and I dot that with r prime, that's going to give me dw dt. Okay, so I need my components, and they were right here. I've got that exponential, x over z times the exponential, negative xy over z squared times the exponential. Forget what it was. It was y of t over z of t. And we've got x over z and negative xy over z squared. Okay. We've got x of t over z of t times e to the y over z. And then we have negative x times y over z squared times e to the y over z. But we need to replace all of these x of t, y of t's, and z of t's with the actual component functions of r of t. So we're taking this and we're dotting it with r prime, which we calculated on the last page. On 1b, we got negative 2t, or we get 2t and then -1 for our y component and 2 for our z component. And remember, x, this is x of t, is given by x squared. Y of t is that t minus 1, and z of t is 1 plus 2t. So those are the parametric equations that we're substituting in on this other problem. So I've got that. I'm just leaving a bunch of space to fill in everything that I need to fill in. And remember, x of t is t squared, y is 1 minus t, and z is 1 plus 2t. X of t is t squared. Y is 1 minus t. And z is 1 plus 2t. Okay, so now I've got everything here in terms of t, and I've got everything over here in terms of t. Now we just want to take a dot product. So remember how dot products work. Dot products always yield scalars. You're just going to take the x component of this vector and multiply it by the x component of that vector. So you'll have 2t times that exponential. And I think I want to factor out that exponential from everything, actually. So I'm going to have 2t times the exponential plus -1 times this, times the exponential. I forgot to put that z of t in the denominator. -1 times that is going to give me a negative t squared over 1 plus 2t. And then we've got the z components we've got to add. So you multiply these, and then you add, and then multiply and add and multiply and add. It only looks a little different on mine because I am choosing to factor out that exponential as I go. So I'm going to have this times 1 plus -1 times that coefficient plus 2 times that coefficient, and all of that is multiplied by that exponential. Now this may simplify actually really nicely, but I will never find out because I'm not going to simplify it. I'm just going to leave it alone. That's dw dt. So it's the change in the value of f of x, y, and z as t changes while we're on this curve given by r of t. Okay, so that is the chain rule. Now here's an application problem involving the chain rule. It says, the voltage in a simple electric circuit is slowly decreasing as the battery wears out. At t equals t0, the voltage is decreasing at a rate of 1.01 volts, denoted by V, per second. Okay, so that's some information. It's a very important information. So I want to write that down. We always want to write down exactly what's given to us. So they're telling me that the voltage is decreasing at a certain rate. So I know that means they're giving me a derivative. And I know it's the derivative of the voltage with respect to time because of the units here. They say it's decreasing at a rate of 0.01 volts per second. So it's the units of the numerator divided by the units of the denominator. Now it also says it's decreasing, so you know that that rate of change should be negative. Okay. It also says the resistance R is slowly increasing as the resistor heats up. Okay. And this is all evaluated at t equals t0. At t equals t0, the resistance is increasing at a rate of 0.03 ohms, denoted by the capital omega, per second. So resistance is increasing at this rate, so that's change in resistance with respect to time. At t equals t0, it's given to be positive 0.03 ohms per second. I'm just taking this sentence here and I'm translating it into that fact. It says using Ohm's law, or use Ohm's law to find the rate of change of I, the current I, at the moment when the resistance is 400 ohms and the current is 0.08 amps, then provide a physical interpretation of your answer. Okay. So let's focus here. What is it asking us to find? We're going to use Ohm's law. Okay, V equals IR. It's important. We should probably write that down. To find the rate of change of the current I at a particular instant when the resistance is given by this much and the current is given by that amount. Okay, And then we want a physical interpretation. Okay, so I want rate of change of the current I. So that means I want di dt. Well, this is just saying voltage is equal to current times resistance. If the voltage is changing with time and R is changing with time and V and I and R satisfy this equation, then we expect I to change with time as well. And we're asked to find the rate of change of current at that moment when the resistance is this and the current is given by this amount. Okay, well, let's see. If I want this, I'm looking for this. I think what I need to do is I need to take this equation, Ohm's law, V equals IR, and I need to solve it for I. Because I'm thinking of I as depending on R and V, just temporarily. We can, of course, switch perspectives. We can think of any one of these as the dependent variable. Divide both sides by R, or you can call that V times R to the -1. Well, according to the chain rule, if I depends on two variables, V and R, the derivative of I with respect to t should be the partial of I with respect to V times dV dt plus the partial of I with respect to R times dr dt. And if you're wondering, how did I get that? Well, I know that I depends on two variables, V and R. So that means my chain rule is going to have two terms. And I'm looking for the rate of change of I, just in general. But if we are given the rate of change of volts and some number of volts per second and the rate of change of resistance and some number of ohms per second, then I'm pretty sure when they say rate of change, they're talking about the change in current every second. Okay, so that's what we're calculating, and this is how we're calculating it. It was a function of two variables, so the chain rule has two terms. So we just need to do some calculations. We actually have dV dt and dr dt. They gave that to us. We just need to find the partial of I with respect to V and the partial of I with respect to R at the given values of I and R, and then substitute. Okay, so we've got Ohm's law, and then I'll just call it I naught and R naught. The I value that was given to us is 0.08 amps, and the resistance is 400 ohms. Call that R naught. Well, I was not given V, but I can find V. V is equal to IR. So I can just take this 0.08 amps and multiply by the 400 ohms. And that's just 32 volts. Okay, so I've got all these values. I need to find these two partial derivatives now. Let's find the partial of I with respect to V. And I'm going to use this form. Well, as far as we're concerned, when we're taking a partial derivative, that R is a constant. So this is just the derivative of a constant times V. The derivative of a constant times V is just the constant. I also need the change in the current with respect to resistance. Partial derivative. Let's do the same thing again. This is a constant times R to some power. Bring down the constant. The derivative of R to the -1 is negative R to the -2. So I can rewrite those this way. And then if I want to find the values of these at these particular values of I and R, I can substitute those in. So let's just say at this value for I and this value for R and this value for our voltage, let's find those two partial derivatives at that moment. So I get 1 over R. So it's 1 over 400. And the units for this are going to be the units for the numerator over the units for the denominator. So this will be amps per volt. And for this one, I want negative of the voltage, which is 32 volts, divided by that resistance squared. So it's 400 ohms squared. And let me get my calculator for that. Probably shouldn't need a calculator for that. That's just 16 with 4 zeros, but it's okay. So I have negative 1 over 5,000 units of the numerator over units of the denominator. So that's amps per ohm. So we're going to take these two numbers, we're going to substitute them in over here. So at that moment, at T naught, at that particular time, the changing current with respect to time is given by this. We'll have this value, which we just found to be 1 over 400 amps per volt, times dV dt, which is negative 0.01 volts per second. Now what this is going to give us, just this first term, it's going to give us the change in the current with respect to time if the only thing that was changing was that voltage. When we multiply these together, the volts reduce, and we just end up with this. I'm going to use the decimal approximation now. This is negative 2.5 times 10 to the negative 5th amps per second. That's just for this term. We're going to do the same thing for the second term. Changing current with respect to time, or excuse me, resistance with respect to time is at 0.03 ohms per second. And then this changing current with respect to resistance, it's right here, negative 1 over 5,000 amps per ohm. So when we multiply those together, we get actually a negative 6 times 10 to the negative 6 amps per second. So resistance is increasing, voltage is dropping, and as a result, the total change in current due to both of those things happening at the same time is this minus that. Which is negative 1.9 times 10 to the negative 5th amps per second. So it says, provide a physical interpretation of your answer. I ask you specifically not to talk about slope. Yes, derivatives represent slope geometrically, but that's not what we're talking about here. This is the current, it's dropping. The current is dropping by this many amps per second due to the change in V and the change in R. Okay, that's it. All right, then we got one last problem. Here we're given Z. We're told Z is a function of X and Y. And we're asked to use implicit differentiation to find these two partial derivatives. Now, generally the way this works is we're going to take this equation and we're going to move all the terms to one side. So we've got a 5xy plus x times natural log of 4y minus z cubed equals 0. And we're going to call this f of x, y, and z. Now, as we talked about in class, the partial of z with respect to x is given pretty simply by this formula. If this is our function of 3 variables, I take the partial of that function with respect to x and the partial of that function with respect to z, I multiply by -1 and I divide like this. Similarly, the partial of z with respect to y looks like this. Notice we have the partial of the dependent variable in the denominator and the partial of the independent variable that we're interested in the numerator. So all we have to do is find those 3 partial derivatives and then we're good to go. So let's look at this. The partial of f with respect to x, there are no x's there, so that's 0. This is a constant times x as far as we're concerned. The derivative of a constant times x is just the constant. And that doesn't have any x's in it. So the derivative of that with respect to x, if y and z are constants, is 0. So we end up with a negative natural log of 4y in the numerator. In the denominator, we want the partial of this with respect to z. So that's a constant times z. The derivative of a constant times z is just my constant. There are no z's in this. The derivative of that with respect to z, if x and y are constants, is 0. The derivative of that piece with respect to z is, of course, 3z squared. So that partial of f with respect to z, that's going to show up in the numerator, or excuse me, in the denominator over here as well. Now, for this one, I need the partial of f with respect to y. So I treat x and z as constants, and I differentiate with respect to y. So this is just a constant times y. The derivative of a constant times y is the constant. 5 and z are being treated as constants. Now here I've got a constant times a function of y. So we bring our constant down, and then we take the derivative of this function of y. Well, that requires the chain rule. The derivative of log of a function of y is 1 over that function. And then we multiply by the derivative of the inside with respect to y, which happens to be 4. And those 4's reduce. And the derivative of z cubed with respect to y is 0. So this is our answer. Probably want to clean it up. I don't like to have those complex fractions. So we'll multiply everything by y over y. And then we'll distribute that y through to both terms up here. And we'll get negative 5yz. And the y's reduced there, plus x, all divided by y times 5y minus 3 times z squared. Okay, so that is the partial of z with respect to y. It's really easy. It's much easier than it was in Calc 1 when we're using implicit differentiation. That's the partial of z with respect to x. It's just a formula that we can use, we can apply now that we know our partial derivatives. And I showed you in class where those came from.